Okay, so this is radioactive decay part 3. Now we want to look at how they sometimes represent radioactive decay. So these were our boxes from radioactive decay part 2 video, and sometimes they represent it this way. They'll show you, a diagram like this, a box like this with, certain number of boxes, or maybe it's a certain number of circles, or maybe it's a bar type thing with a certain portion of the bar filled in to represent that's what's been decayed and what hasn't changed and all that kind of stuff. But the other way that they sometimes will represent radioactive decay is graphically. So we've got, and I think I'm going to have to scroll it down so that we can see it all. Okay, so here I've got my graph that's all about my vertical axis says the percent of carbon-14 and nitrogen-14, and I have it as percentages going from 0 up to 100. And then my horizontal axis, my independent variable, is the time, because in thousands of years we are going to do carbon-14 and nitrogen-14, so 5,000, 10,000, 15,000, 20,000, and so on. So they might show it to you graphically. So when I first start out, I'm going to graph carbon-14 first. I've got 100% carbon-14. Okay, when the object is first made, whoops, where's my 100? There it is. When the object is first made, when it's 0 years old, the object contains all of the radioactive carbon-14 that it's ever going to contain in its lifetime. Okay? And then after one half-life, 5,700 years, it's going to contain 50%. So there's my graph line for 50%. After 11,400 years, now I'm down to 25% carbon-14. 25% carbon-14. And then 17,100 years, I'm down to 12.5% carbon-14. 12.5% carbon-14. And then 22,800 years, I'm down to 6.25% carbon-14. And then after 28,500 years, I'm down to 3% approximately, 3% carbon-14. And then 34,200 years, I may be down to 1.5% carbon-14. And then 39,900 years, I'm down to 0.78%. So I'm going to get really close to 0, but I'm never going to get there. So if I were to connect my points in a nice, smooth, curved line as best as I can, my line would get really close to 0, but it would never get there. Okay? So then I can also graph the percentages of nitrogen-14. So at time 0, I had 0% nitrogen-14. None of my radioactive material had decayed yet. After one half-life, 50% was now nitrogen-14. After two half-lives, it was up at 75% nitrogen-14. After three half-lives, or 17,100 years, now I'm up at 87% nitrogen-14. And then four half-lives, 22,800 years, I'm at 93%, 93% nitrogen-14. And then after five half-lives, 28,500 years, I'm at 96% nitrogen-14. And then after six half-lives, 34,000 years, 34,200 years, I'm at 98% And then after 7 half-lives, 39,000 years, I'm up to 99%. It's hard to tell. I may have gone a little bit above my 100 line. But then when I connect those in a graph line, that's sort of what should look like that. So there's my percent nitrogen 14, and here's my percent carbon 14. And that graph line, that graph is pretty much the same graph you get for whatever radioactive isotope you're looking at. The only thing that's going to change are the numbers on the horizontal axis, the amount of time that passes by. Each radioactive isotope has its own half-life, its own amount of time that it takes for 50% of it to change. So the graph will still look the same, it's just that the numbers along the horizontal axis will change, okay? So a graph is another way to represent radioactive decay, and if we wanted to know how long it takes for carbon-14 to decay, we could read it right from the graph. We'd go to 50%, and then we would read down and estimate how much time that is. So you can read information from the graph pretty easily if you remember that idea that every half-life, half of the radioactive material will decay or change into the stable daughter product. All right, so now you're going to work on CASEL learning questions. So open up the CASEL learning assignment and answer those questions all about radioactive decay.